When we think about natural disasters, we often think first about earthquakes, or storms, or floods. One disaster that often gets forgotten are heat waves. In 2003, a heat wave in Europe killed 30,000 people. More people than ever are moving to and living in cities where heat waves are the most dangerous, in part because of the UHI. The urban heat island effect, or UHI, is a phenomenon where developed areas are much warmer than their surroundings. This can happen because asphalt and concrete soak up heat and cool down slowly, because of a lack of shade, and for a variety of other reasons. But there are still questions about the urban heat island effect. How urban is urban? Does the heat island effect exist in towns or even in neighborhoods? And when we get down to the scale of something like a neighborhood, what matters? Does the layout of the neighborhood itself have an effect? What about the land around it? This semester, myself and 3 other students in Dr. Anika Bratt's urban ecology course researched the significance of the urban heat island effect on a neighborhood scale in the area of Davidson, North Carolina. Our study involved in what ways the composition of the neighborhoods affected a potential UHI, and in what ways the adjacent land type affected a potential UHI. To start off, our group selected 8 neighborhoods from the Davidson-Huntersville-Mooresville area. We loosely define neighborhoods as a planned development of single-family homes. A lot of these have clear borders, which makes them easier to study spatially. Using Google Earth to look around, we chose 4 neighborhoods bordering Lake Norman, and 4 neighborhoods not bordering the lake. Within each group of 4, we tried to diversify the types of neighborhoods. Some very dense, some spread out, some more forested, and some not. After outlining all 8 neighborhoods, we transferred the borders to QGIS, a robust and open-source digital mapping program. For each neighborhood, we were trying to classify how different characteristics affected neighborhood temperature. But how were we supposed to find the temperature at a scale of something as specific as a neighborhood? Enter Landsat 8. Landsat 8 is an imaging satellite launched in 2013 as a joint project between NASA and USGS, the United States Geological Survey. It creates images of the Earth's surface where each pixel is a square of 30 by 30 meters. Its captures are freely available online, and it doesn't just capture visible light. It also measures the emission of infrared light, which allows us to use it as a proxy for surface temperature at very specific scales, like that of a neighborhood, for example. By taking the outlines of our neighborhoods and overlaying them on Landsat temperature data, we can determine the average temperature of each neighborhood. Now that we have temperature, our dependent variable, we can analyze the characteristics of the neighborhoods in similar ways. We already know, based on where the neighborhoods are located, whether they're adjacent to water, Lake Norman, or not. We also wanted to characterize each neighborhood by the amount of vegetation cover, and by the density of houses. We measured vegetation cover in each of the neighborhoods by calculating something called NDVI, Normalized Difference Vegetation Index. For each 30 by 30 meter cell of Landsat data, we can calculate NDVI, which is a measure of the richness of vegetation. Higher numbers means that there's more rich vegetation, where lower numbers means that there's less. Determining house density was easier. We just looked and counted. Overall, we found similar relationships between temperature and NDVI between both kinds of adjacent land type neighborhoods. As average NDVI, or vegetation in cover, increased, mean temperature decreased. Feel free to pause the video for a better look at the graphs. Inversely, as the number of houses per acre increased, mean temperature tended to increase. We also saw this happening similarly between neighborhoods on the lake versus neighborhoods elsewhere. When it comes to comparing the 2 different types of neighborhoods, lake adjacent versus forest adjacent, the 2 groups had very similar average NDVI and house density values. When it came to temperature, the 2 groups had slightly different average temperatures, but not quite significantly different. What does this mean? Our results definitely support the notion that the composition of a neighborhood area has an effect on its temperature. Vegetation cover is one example. It seems to be effective in providing cooling services, and decreased vegetation cover is present in denser neighborhoods. Our results don't support the idea that neighboring land types can affect the temperature of individual neighborhoods. Although our results were not significant, we did see a non-significant difference with only 8 neighborhoods, so further research might analyze even more neighborhoods. In what other ways could future research on this subject proceed? When I was creating maps of the temperatures of individual neighborhoods, I noticed that more compact, rounder neighborhoods seem to have different temperature distributions than more thin, stringy neighborhoods. Is this a significant difference? Knowing more about this could be valuable for builders and planners. Clearly, there's still a lot to find out here. Stay cool and stay safe, everyone.